All right, welcome to today's seminar. Even though with a less full room, I believe we'll have a very interesting experience and a conversation following the seminar. It's a big honor to introduce our colleague from USC, Professor Ketan
Savla.
Savla. Ketan is a professor in civil and environmental engineering, also electrical engineering, electrical and computer engineering at the USC. His training background is very diverse, spanning mathematics, mechanical engineering, electrical engineering, and so on. And so today, we look forward to hear his perspective in related to data-driven transportation system decision-making and optimal control. Jason is yours.
Thank you, Yo.
We have until like around 2:30-ish for the presentation,
Okay.
and followed with maybe 20 to 30 minutes Q&A.
Sounds good. Thank you. Thank you all. It's my first time in Davis, and ever since I got down at the airport, the openness of the space was really what I liked coming from LA. So my understanding is this is a very broad audience, which is always a challenge. So I have something on slides, right? But I'll try to keep it at high level when I speak. But again, it's best if you interrupt me if something is going completely tangential before it's too late, right? And I'll try to kind of summarize my main points once in a while. So what I want to present today under this generic title is a couple of case studies, one from the supply side and from the demand side, on how when you switch from model-based to more data-based kind of perspective, how things could actually become more interesting. And I'll be more precise in that sense. So I must say that Okay, so this work is funded by NSF and US DOT through our Veterans Transportation Center at USC. And I also have a company, I'm a co-founder of a company called Intelligent, where we do smart traffic signal control, which we're deploying in multiple cities right now. I'm not going to talk about that explicitly, but I'm happy to talk about that offline for those of you who are interested. So that includes connected vehicles and all of that fancy stuff. So I like to start by giving a broad overview of where I'm coming from as a researcher, right? So as you mentioned, I'm not a core transportation person by training, but I bring tools outside transportation, specifically control theory, dynamical systems, and operations research into transportation problems, right? So here are quick snippets of some of the problems that I've worked in the past, but I will not be talking about explicitly. And there's like some kind of a common thread in these problems, which I really like. So one of the problems that I studied way back had to do with logistics problems, where let's say you have drones who want to service certain points which are realized in the space of interest, right? So this could be an alarm that has been set in a sensor, and the drone needs to go and kind of do a close inspection, or these red dots could be something that needs to be picked up by a drone, right? For example, so pickup and delivery would fall within this domain. What I was interested in, so some of you may know of this problem as vehicle routing problems, right? What I was interested in was the dynamic version of that, where these red dots keep popping up in real time. So you do not know in advance where these dots are going to pop up. You have some statistical understanding, right, of where this could be from historical understanding. And in real time, you have to keep rerouting these vehicles, right? Because you already had a plan for them to go and visit some points, but because new points have popped up, you need to replan. Right, because you were originally planning to go this way, but now there's a point right here. So you need to kind of maybe accommodate that if it's not too late. While this problem was studied in the operations research community for a while, my take on this problem was to explicitly take into account the motion constraints of these vehicles, right? So all of a sudden, when you have to take into account that these drones, for example, have radius of curvature and other kind of constraints, then the optimal order in which you have to service these points becomes interesting all of a sudden. Just because a point is close to you doesn't mean that's the next point you should visit, because maybe that point is behind you. And then there's a point which is further ahead, but right in front of you. That might be the closer to you, right? So, really the way I think of this problem and several other problems is there is a universal framework of queuing systems within which I think of these problems. So think of these red dots being generated by some external process. And then these my drones or vehicles are servers, which are servicing these demands. The challenge is for those of you who have taken any class in queuing systems, usually the service time of the server on a particular job is assumed to be not correlated between successive jobs. If the jobs are not correlated, the time it takes for the server to process those jobs will not be correlated. All those assumptions break down in this example. And so this kind of state-dependent queuing systems appear in many applications in transportation systems. So vehicle routing is one. Other is something that I'm doing recently is doing RAM metering at the microscopic level, right? So there's a lot of work on RAM metering using macro models, something that I'll be talking about in length in detail. But if you go to see actual RAM metering, you see one green per light, one vehicle per green. That control is really at the micro level, right? And with all the connectivity and all of that, there's a need to kind of formally or rigorously think about controlling RAMs at the micro level when you have V2X communication between the RAMs and the vehicles. So we again cast this as a queuing problem, right? Where the road itself is acting like a server, which is processing all the jobs, but then you control the entry into the server, right? Believe it or not, I've taken this perspective even beyond that into human systems, right? So think of a human as a server, but this is a very unconventional server because the time that the human takes on a job, if one job is going to take a really long time and frustrate the human, then even if when the next job has nothing to do with the previous job, but because of the frustration that the person has or the fatigue that the person has, it's going to correlate the service on the job, right? So these are samples of what is hopefully leading to a very rich notion of state-dependent queuing system, right? So this is something that I have published a lot on and I've worked a lot on, but that's not something I'm going to talk about today. Okay, and similarly, there's some work on control infrastructure networks that I've also done. So what I want to talk today are two things, okay? One, and both the problem themselves have been around for a while, but I want to revisit them from a data-driven perspective, as I mentioned. So the first problem is more on the supply side, which is coordinated RAM metering, right? So I'm guessing many of you are aware of RAM metering, either if you have studied explicitly or being in California, you must have been exposed to RAM metering, for example, visiting Bay Area, for instance,
So
right?
we have right 80
Okay.
there is like Mace Boulevard and yeah, so they should see.
So the problem that I'm going to really ask, the questions that I'm going to ask here is, so that the typical RAM metering algorithms, they require so of course it's a closed loop algorithm, which means the RAM metering algorithms, they sense traffic and in real time they decide the duration of green and red, right? So that's what the RAM metering algorithms are. In practice, that's how they're supposed to, but if you go to the academic literature, many of them rely on the availability of queue length, okay? This is what we call as state-dependent or state feedback RAM metering policies, okay? There are some which use directly the occupancy information from these loop detectors, which we will call as the output feedback RAM metering control policies. So in this talk, I'm going to revisit some of the output feedback RAM metering policies and see to what extent do they provide good enough performance or not. And I'm going to claim that they do not. And I'm going to provide a RAM metering policy, an algorithm that is going to give the maximum possible performance with respect to a certain flow metric. It is going to maximize the efficiency of your freeway as a system by using the information coming from the sensors in an appropriate way, right? So that's a data-driven framework. So as a subtext to that, the question is really, do we need sensors per cell? What if some of the sensors are faulty or they break down? Will my performance still be robust? And the point again we'll make is that the algorithms that we are going to design, they'll be pretty robust, okay? And also inherently in some of these algorithms that exist in the literature, they need to know some specification of network parameters, okay? So for example, what is the capacity of the freeway, for instance, right? There are a few other parameters associated with the traffic flow models. Do we really need to know all those parameters, right? Or can my algorithm, by making observation, can learn and can adapt to those parameters, right? So those are the questions. So like, really, do we need to stick to model-based paradigm when we do RAM metering? And then the other problem that I'm going to look at is on the demand side, okay? and more specifically on a very special kind of advanced traveler information system, which provides randomized private route recommendation to the travelers from the perspective of steering their decisions towards social objective. So here I'm going to adopt a framework that is emerging in the economics and game theory community called information design, and I'm going to explain what that means, right? And I'm going to specialize it for this problem of route recommendation. And as soon as you specialize that framework to to route recommendation, you immediately run into assumptions which are not practical. For example, in order for that framework to work, you need to know a lot of private information about the drivers for that whole thing to work. And the question I'm going to ask is what if you do not know that private information, right? Or what if, and also what if the drivers themselves are either AI agents or drivers themselves who are not perfectly rational, but they themselves are learning-based models. They're just based on simple rules of thumb, the decision they make. How can we ensure that they will comply with your route recommendations? Right, so these are the broad questions that I want to ask today. Okay, so overall, the idea is by default, when you go to data-driven things, you tend to do sequential things. You first estimate from data and then use that estimate to control. So this is what I call as a sequential approach. It's a natural approach because we have a lot of work here and we have a lot of work here. So why not just combine this and put them in a sequential manner? So in this example, if you have nice algorithms that use Q lengths, okay, why not first estimate the Q lengths from the data and then use the estimate of Q length to drive your algorithm, right? So that is not, I mean, it's a fair approach, but you will see that is not necessarily the optimal approach. So we want to go directly from data to control without necessarily worrying about the estimate if it doesn't need to be. Okay, so here's a preview of the results, okay? So for the first setup, it's known in the literature that if you want to do this data and estimation and then control perspective, then you need at least one sensor per cell to do a good job at a high level. And I'll be more precise what that means. What we will be able to show is that with the same infrastructure in place, but with a careful design of how you use that information, okay, you can actually get a good maximum possible throughput, maximum possible flow of traffic with much fewer sensors. In fact, we'll be able to guarantee it even with no sensors on the main line. Only with sensors on the ramp, okay, we'll be able to guarantee maximum throughput. So for example, the lines here show so on the y-axis, you have the total number of vehicles in the network at any time, including the ramp. And on the x-axis is time, okay? So each of this line is the evolution of the total occupancy in the network versus time under different sensor scenarios. Okay, so this one is when you have only one sensor working, sensor number one. Okay, so there you have the worst performance, but still after initial transient, you recover your flow. Okay, and then when you have two sensors working, 1 and 2, you have a slightly better performance, and when you have more sensors, you have even better performance. So our algorithm allows you, well, for no matter how many sensors are missing on the main line, it still recovers its performance after long run, okay, in terms of the throughput. Throughput would be, so throughput, as I'll define shortly, so the worst thing that could have happened is this line kept on increasing, right? That would be the case when just there's a huge spillback and it's just growing over time, right? So conventional algorithms, which I'm not plotting here, once enough sensors have broken down, the occupancy of vehicles, there could be a bottleneck which never gets resolved, right? Whereas under our algorithms, that will never happen. Okay, and then I'm going to skip this and I'll just give a preview when I get to this part. So let's dive deeply into this first part of the data-driven RAM metering, right? So here's a very sparse sampling of the literature on this topic, including one from Professor Zhang here. So roughly speaking, these RAM metering algorithms, at least from my perspective, they can be classified as one of the two types. Okay, one is so-called regulator-based. What that means is there's a certain ideal occupancy that you want in the cell, and you try to achieve that, right? So there's a certain baseline. It's like if there are enough. So for those of you who know the fundamental traffic diagram, there's a peak of that fundamental traffic diagram. You want to maintain the occupancy around that because that's where you get the maximum flow on the traffic, right? So these fall roughly in the left column here, right? So one of these, for example, Alinea, has been deployed in practice also, okay, in several parts of the world. And these are simpler in the sense that they're like closed form policies. You can write down the formula for the duration of green light as a function of the occupancy on the road and things like that. This is the linear, right? And then there are the ones which are a little bit more sophisticated, right? They use the information, they observe, they input the information, like coming from the sensors, and they solve some kind of an optimization problem before deciding how much green should be given to each ramp at any time, right? So these are the optimization-based approaches. And so these are roughly the class of policies, algorithms that exist in out there. Ours will fall roughly here. Okay, that's where ours is going to fall, and yet it's going to beat this kind of stuff. So here is now getting a little bit more into the weeds of this algorithm. So this is what I call state feedback RAM metering controllers, right? So what it does is let's assume for now that it has all the model parameters, meaning it knows the geometry of the freeway, what is the speed limit, something that we call the wave speed, capacity limit, and things like that. It knows all the parameters which are fixed for the transportation system. On top of that, it has access to real-time occupancy information from the sensors. Okay, so there's a class of algorithm which will, let's say, or rather, so actually in this case, let's say it has the word state here refers to queue length. So if there are sensors here, for example, cameras, which directly give me the queue length, then there are certain algorithms which the literature claims that work well, right? So these are called state feedback control policies, but they work only in simulations in some cases, and they do not really explicitly provide any guarantee on throughput. Okay. On the other hand, there are now more practical algorithms which do not necessarily assume you have access to cameras so that you can have counts of vehicles, but only you have access to these loop detectors, right, which only measure occupancy. What they do then is first estimate traffic state, meaning estimate the queue length, and then feed to the regular algorithms. Here again, the guarantees are not really tight. I mean, there are algorithms, but you cannot really guarantee that if you deploy this, you're guaranteed to get a certain performance. Okay, and then there are this Alinea algorithm, which has been deployed in practice, which does not necessarily bother with an estimation step. It directly takes as a measurement and directly does control, right? So this is something we want to do, right? And we want to achieve if possible. But the guarantees that this algorithm has only guarantees that the flow will be nice on the main line, but does not provide any guarantee on how many vehicles will be stuck on the ramp, right? So the focus is really on the main line, whereas we want to have more of a system-wide perspective. You also want to care for people who are waiting on the ramps, right? Because you could have an empty freeway, but everybody's stuck on the main line, stuck on the ramps, right? So here's the performance metric that we'll be interested in, right? So I've been using the word throughput many times, and this is our formal definition of what we call throughput. So this is the quantity we want to optimize when we design an algorithm, right? And people use through the word throughput in different ways, but here's how we are going to use. So if you look at a section of a freeway, there are several entry points into the freeway, right? So in this example, there is one coming from upstream, and there are these 2, 3, 4, 5, 6 that are coming through ramps, right? So I'm thinking of flow coming in exogenously through 6 entry points, and they collectively form this vector lambda, let's say, right? Now, so these are I cannot control. This is coming from outside world. What I can control is, except for the first one, for 2, 3, 4, 5, 6, I can control at what rate they can enter my freeway, right? This is where my algorithm will come into play. Now, for the same boundary condition, depending on what algorithm I choose, I could have spillback, I could have a bottleneck somewhere or not, right? So I would say my given boundary condition can be sustained by my algorithm, or if it's in the throughput region, if every on-ramp is undersaturated, right? Meaning there's no queue being built up, right? So the boundary flow will eventually get into my system, will get into my network, right? So I want whatever policy I design, whatever algorithm I design for RAM metering should have as large as possible value of this lambda. That's what I want, right? And I'm going to compare different policies with respect to this metric. That's really the idea. Okay, and so again, this would be undersaturated and this would be oversaturated, right? So I want a policy, an algorithm which is implemented at each of these ramps, so that for maximum possible demand that's coming towards the freeway, I will avoid this situation. That's really what I want practically, right? So that's why it's a supply side kind of a strategy. So here is now the formal model that I'm going to use for that purpose. So I'm going to start with model-based. In the interest of time, I'll describe details only for that one. So here I'm describing a dynamical model for how traffic behaves for a given rate at which traffic enters from different ramps, right? So some of you probably, this is a very standard model in traffic flow theory called the cell transmission model. So I'll just go at a high level here, but I just want to note we capture the capacity drop phenomenon here also, right? So for those of you not familiar, this describes, this is basically a mass balance equation, right? So X here, superscript M means mainline, superscript R means on ramp. X denotes the queue length on a particular cell. So if you see, I have 6 partitions of my, here I have one, well, I have several partitions here. Each partition or a cell is associated with one X, right? That denotes the queue length, the number of vehicles at any time in that particular cell, right? So X1M, for instance, will be the number of vehicles in that section at time T, right? So the dynamics of that quantity is simple mass balance equation, right? So X at T plus 1 is how many vehicles were before, plus how many vehicles enter from upstream, plus how many vehicles enter through the ramp, minus how many vehicles just kept moving to the downstream. Simple mass balance equation, right? Now, how these quantities inflow and outflow depend on X itself is what the fundamental diagram gives, right? So they have a relationship which has certain parameters in them, right? So for low values of X, the more X, the more X is, the more vehicles is, the more flow you have, right? But once the value of X is very high, once you start approaching congestion, the flow starts dropping. So again, for low X, for small values of X, this will be the outflow. Okay. So the outflow term here is the minimum of 2 quantities. The first quantity is called the demand. The second quantity is called the supply, and the inflow is just a factor of the outflow term. So what you want to take away from this slide, for those of you who are not really familiar with the traffic flow theory concepts here, is that this dynamics, this is a model that has been well established and calibrated for traffic flow, right? And the question now is, we want to design U. The U is what is designed, is coming from the ramp metering algorithm. So if U is 0 for a particular ramp, that means that ramp is always red, right? And if U is, let's say, 1, then that ramp is always green. So U is something we can control, and that U is then going to control my X and everything, right? So my U is the knob that I have that I can use, yeah.
So Ketan, you're assuming the exit flow is 1 minus beta times the
Exit flow, yeah,
Okay.
exactly. So beta are the turning ratio,
turning ratio.
turning ratios, yeah, those are what they are. So right now I assume that whatever U I want to design knows these betas and the slopes and everything. So that's what I call as a model-based approach, right? But the twist here is that, so until here is something that people do, I'm going to now start assuming that maybe I do not observe X directly. Okay, so remember X is my Q length. Okay, maybe I observe only a subset of that. So my C matrix here is a diagonal matrix, let's say. I only observe, and without loss of generality, you can assume this is either 1 or 0. Okay, so for example, if there's only 1 here, then I only observe the first sensor, for instance, right? So my U has to decide its ramp metering by looking at Y, not by looking at X. Okay, so that is the twist I'm bringing in this problem. Okay, so that's the problem, right? So I want to design U knowing Y, so that for maximum values of lambda, my X on the ramps remains unsaturated. That's really the problem. Okay, so for the next few slides, I'm going to describe how we do that, how we design such a U, right? So the challenge here is some of the X I cannot observe. That is the challenge. Okay. Now, some of the mainline X I do not observe because the sensors are either faulty or new.
And you don't observe X, you only observe Y. So the policy, the control policy will depend on Y.
Right.
But do you still use the relationship between X?
Yes.
Okay.
Yeah,
So
I use
that's
the
still
dynamical
part of-
model. That is,
yeah,
in fact, that will be part of it. Yes.
Okay.
So this in model-based approach, I'm using all of that, right? And in fact, even in model-free, I do not know the parameters, but I still assume the CTM dynamics underlying. right? So again, the challenge is if X were all known, then let's assume that if X were all known, then I know how to do these things. The challenge is what if when I do not know X? Okay, I do not know some of the freeways section, how much congestion is there, right? Now, even without knowing anything, I know they're within some bounds, right? Either one extreme is it's empty or it's completely congested, right? So already have some uncertainty understanding of where the values of X will be, even if I do not see them, right? But that maybe that's too broad of an uncertainty set. So what we are going to describe now is a way of propagating this uncertainty in a very smart way, okay? So that when we get information, we update it, and we'll do this in a slide, I believe in a good manner. So the way we do it is, so again, when we start running our algorithm, okay, let's say there is one particular cell on which I do not have access to the sensor. I know that it's going to be either between the jam density or 0. Okay, its value is going to be between jam density. In fact, for the entire network, this is where the state is going to be somewhere in this hyperrectangle. Okay, some of the states I know precisely, but others I know for sure they are here. So the way I'm going to do is I'm going to define a new what we call as a lifted dynamics. Okay, so I'm going to augment my model with additional variables, and the variables will be X and Z, where now my original variable will act like an upper bound in some sense of my uncertainty interval. And another variable that I add, Z, will act like a lower bound on the uncertainty interval. So this, when you run this dynamics, this is a predictive model. This model will have the property, the way it's constructed, I'm skipping details for lack of time here, but it's prediction, it's going to evolve. So the value of X and Z at any time coming from this model will give you guarantee the uncertainty set of my state at any time. By construction, this model has that property because the way it's designed, right? So even if you do not know anything, right, for a given value of RAM metering, so RAM metering is something that you design, right? So you know the values of U, you do not know the values of X, right? So if you knew the values of U, this is the uncertainty in your state will be guaranteed by the box, which is defined by these 2 points coming from this dynamical system. So that's a contribution. This is something we call the embedded cell transmission model. Okay, so we take our original traffic flow dynamics and we lift it into a higher dimensional space, because once constructed properly, it works very nicely for uncertainty quantification here. Okay, so that's the uncertainty quantification part, right? So this is a very good part, but now I can do this for a given control policy. For a given control, I know how to do uncertainty quantification, but our objective is to actually design optimal control, right? And this is where now we combine measurements with control in the following way, okay? So for those of you who have, who have some background in control systems, this is what is called as a model predictive control framework. It is a very popular framework for doing optimal control. So like any good estimation control approach, there is the update step. When you get new measurement, you update your estimates. You do control based on your estimate, and then you move to the next step. This approach has a similar flavor. So at time t equal to 0, let's say, okay, you wake up, right? You have very large uncertainty, right? Either everything is congested or everything is empty. That's your uncertainty set. You get measurement from some sensors, okay? And for the cells on which you get exact measurements, okay, the uncertainty becomes 0, okay? So step 1, you update your uncertainty based on measurement you get, okay? Now in step 2, based on the uncertainty what you have, we have a predictive model which knows that for a given U, it will tell you exactly what the uncertainty will be in the future, okay? So we design our optimal U that maximizes the objective. So this is what we design. So we are going to look forward t time steps into the future, okay? And we are going to choose a U that minimizes basically sum of the occupancies on all the cells, which is called the running cost and the terminal cost, okay? So I design my control that minimizes certain notion of number of vehicles in the predicted number of vehicles into my freeway for the next t time steps. That's how I'm going to design my U, okay? But that prediction now is based on this model, because I do not know exactly what my values are. This is my estimated values that will happen.
So I wonder how, so you have the Z providing the lower bound but they're not playing any role in the
So
objective function.
cost function Z is not appearing, you are correct.
Yeah.
So I'm optimizing for the worst case in my cost function because X is my upper bound, right? So I'm optimizing for the worst case. But Z does appear in the constraints because X in the future, my prediction depends on my current estimates, and they depend on this one, right? So this is how you design. If my prediction was correct and I look at the worst case, what kind of parametering will I do for the next T time steps? Let's say for the next T minutes, let's say, right? And what model predictive control does is it plans for the long horizon, but it only executes the first step and then it replans again. That's the beauty of model predictive control, okay? So in this case, what we'll do is we compute our optimal U for the next T time steps, okay, next uppercase T time step, but I only execute for the current time T, where I am right now. And then at T plus lowercase T plus 1, I do the whole process again. This is what I'll keep doing at every time step, okay? So at every time step, I first absorb the new information, reduce my uncertainty set as much as I can, okay? And then design the optimal control for the next T time step based on a predictive model, okay? And then execute the first control for the next time step and just keep doing it all over again. This is what the algorithm is for the rhyme metering algorithm, okay? Now here, there are a few parameters that I have to choose, right? How long of a horizon should I be planning for in the future? The uppercase T here, okay? Intuitively, the longer you plan for, it's better because you're really looking far into the future, right? You're planning on a longer horizon is better than planning on a shorter horizon because you're forecasting whatever congestion that could happen in the future, right? But the challenge is that the bigger the value of T is, the more complex, the more computation intensive this problem becomes because eventually this is an optimization problem, right? So the bigger the value of T, the larger is the size of the optimization problem. Yeah.
Not only that, but also the more into the future, the less accurate your prediction is. And that will affect the performance as well.
Right, so that too. So if the cell transmission model is correct, then, which is an if, right? Then we are guaranteed that our predictions will contain this uncertainty set that is defined by our box will contain the actual set. So if there is more uncertainty on top of the cell transmission model, then yes, of course we will be, for that purpose, we may not want to plan for long.
Yeah, but the lambda one is the input. You don't have that information. You have to predict in the future. The lambda one, the ones.
That's a good point. So we are right now assuming you're perfectly right. Right, it's an implicit that we know we have access to the demand, the projected demand, right?
Yeah.
But I must point out that if you have a lot of uncertainty, you should still plan for the long run, but you should only execute for small time steps. So because you'll always get a chance to correct yourself. Yes. If you execute only very fast, right? So what are the variations of this philosophy, right? The variations of this philosophy are you plan for long, but then let's say you execute for 5 time steps and only then replan, right? So there are variations of that. The more frequent you redo this thing, the more robust you will be to all sorts of uncertainty. So here we are proposing that you will resolve the whole thing every time step. That's what we're doing. So plan for the long horizon based on whatever information you have, whatever projection you have, but then only execute the first step and then redo the whole thing, right? So that comes at the cost of computation. Yes. So if the computation, which by the way, these are mixed integer linear programs, and for the size of the network that we are saying here, that was not a problem for us.
So your T is typically 5, 15, half an hour?
It depends on the size of the network. Typically, it depends on, so roughly, very conservative estimate is how long will it take if I stopped every car and let the network empty. But it doesn't have to be that.
That's a very long time.
So practically, it's much less than that. I mean, for sure, that will be enough. But when we run the simulations, it is much, much less. But that is how it works.
I feel there's the trade-off. So the control acts in 2 ways. It allows you to increase your information quality,
yes.
Right? Improve your understanding of the uncertainty. it also reduces, increases throughput, reduces the queue. And then what you're minimizing in the worst case could be caused by the actual queue is reduced or your knowledge of the queue is reduced.
Both, actually.
Yeah, so I'm a little bit, unsure about.
So again, that what you're is bringing up is a very good point, right? So the control here, because remember, I do not know my actual state. So if I didn't care about throughput or anything like that, if my objective was forget about the performance, I really want a good estimation of the network state, and I can use my RAM metering to empty everything. And in some time, I know what the network will be because it will be empty, right? So my estimate will be perfect, right? But I do not want to just do estimate. I also want to control at the same time, and doing simultaneously is where the challenging part comes in. So the details behind the design of this is it strikes that trade-off in a very nice way, right? So this design of U does keep shrinking this uncertainty set over time, but at the same time, it keeps moving you towards that control objective of the throughput. If that, I don't know if that answers your question. So
Yeah, because I don't see how it will keep, how it will act on the actual throughput. I can see that the reducing,
oh, I see.
yeah,
So by throughput, again, we mean that this X should not blow up, right? Because what is our concept of throughput? That things should remain undersaturated, right? They should remain within a certain bound. So that's why by minimizing the total X, we are forcing it to remain unsaturated. So by choosing U, that will, in the worst case, our worst estimate of X minimizes our worst predicted estimates of X. Therefore, it will also kind of keep my actual X will also be very small because this X are the worst case ones.
okay.
So that is how it's affecting the throughput. Okay. Okay. So here are some simulations, for example, right? So let's look, we took this network, okay, where downstream we started with a very high congestion, okay? And the demands we set to be very close to capacity, okay? So there's certain capacity of a cross section, and we set this lambdas and the betas and all of that, so that it's very, very close to its capacity, the field, right? If you do not do any RAM metering, if you just let everybody go green, then you lead to saturation. Okay, so there's at least one RAM at which the queues will just keep building up. That's what is going to happen. This is what the Alinea controller will do. Alinea controller, remember, is an output feedback controller that has been used in practice. Okay, if the Alinea controller has access to enough sensors, okay, at least 5, so at least 1, 2, 3, 4, 5 are working, okay, then it does okay. But as soon as, actually, in fact, it needs all 6. But as soon as it has, let's say, any of this or these 4 scenarios, then it will lead to at least one of the queues on the RAMs be growing up, right? So yeah.
Okay, then when the Alinea is local feedback, so when you don't have a sensor, so you use the Z's to feed the Alinea, or you use the estimate. So how you, because like let's say lambda
Good
3, right?
So
It's the feedback is based on the X3.
right.
Right, but then there's no sensor, there's no X3,
right.
and there's X1 and X6.
Yeah.
So do you estimate X3
No.
or?
So that's a detail, and which the answer to it is, so let's say in this case, 1, 2, and 3 are working. So at 1, 2, and 3, I apply Alinea, and 4, 5, 6, I do open loop, meaning
Oh,
always
I
green.
see, so you.
because we could not find any alternative to Alinea. So we apply Alinea only where you have sensors.
Ah, okay, so the
what
other
it
is open.
Others is just you let everybody
This
go.
is not a fully controlled by Alinea, this is.
Yeah, because we do not know how, at least I do not know of a version of Alinea which can compensate if.
Yeah, no, but you would has to estimate based on the 3 sensors what each X would be, and then you can apply
You could,
Alinea
so
there.
we would like to do that, right? But again, because of our results, it's not going to be our policies, because we showed that, as I will show here, it gives the best throughput, our policy. But it would be worth kind of checking the gap, for instance.
Right,
Right.
that way you basically have applied to Alinea to every
Exactly.
one.
No, that's a good point. We should. Okay, so this is what is done in not many places, but some places like when there's no RAM metering, right? This is the phenomenon you'll get. This is when you apply a linear, when you have sensor, you will apply a linear. This is what you would get in this case, right? And a linear again is applied in some cases. So previous one were practical, like this is what happens, is out there right now. This is what will happen if we do sequentially. You first estimate, right? And then you do control. Right? You first estimate, there are many algorithms for estimating Q, and then you apply your estimate to your control using state of the art. Even here, once you have enough number of sensors missing, things become oversaturated, even at this point. And this is yet another, so now you would say, well, maybe this is happening, and by the way, this acronyms mean some state of the art in the controls community where they apply control and estimation together. So MHE stands for Moving Horizon Estimator, for example. Right? So this kind of techniques have been used in the process industry, chemical process industry, for example. They have been successful, right? Not in traffic, but in chemical process industry. So instead of sequential, there is a version of this which does things jointly, right? Even that is not very successful. It improves, right? For example, it's able to tolerate up to here, right? But after that, it again becomes unsaturated. And there goes, now comes our algorithm, which this plot I showed before. Right? No matter how many sensors you have, because again, it's using this estimate in a very proper way, it's able to withstand any number of missing sensors. It gives you maximum two. Okay. So this was all simulation, and again, I'm already out of time. Sorry. So in the interest of time, I'm going to skip the details of the model-free version. Right. So in this case, I assume that I know the lambda, the demand, I know the certain parameters of my network and all of that, but there is a version of this where we also learn this in real time, and that also works fine, okay? And again, this slide says that these are not just purely simulations, we actually have a mathematical proof that actually they work. When they will give the maximum throughput. Right, so our algorithm gives the maximum throughput as long as you have only measurements at ramps. That is needed right now. You don't need anything on the main line. Okay, the model-free version for the proof, we require full measurement both on the main line and the ramp. Simulation suggests we could match this also for the model-free version. Now I realize I'm very close to time, so
Well, we asked questions already, so.
Yeah.
So I'll go a little bit fast before
Yeah.
the next part, at least at a high level, because I think there are some experimental part in
I
the
think
next.
the 240, 45 should be
Okay.
okay,
Yeah,
right?
yeah,
Because
245.
for the ending point is a 3.
Oh, for sure. Yeah. So the next one is now I want to move on the demand side of things, right? So in the previous part, the system planner did not have enough information. Okay, they didn't have enough sensing, didn't have enough information about the model, blah blah blah. Here, let's say the system planner has a lot of information about the physical stuff, but cannot really predict how the agents or the decision makers are going to respond. Okay, so in other words, the agents themselves are data driven. The data driven part is now in the agents, the drivers who are driving, right? So here, I'm going to adopt, and maybe some of you are not familiar with the so-called information design framework that is gaining popularity as a recommendation generation platform. Okay, so the whole idea of information design is that there's something called principle, which is trying to influence the decision of the agent. And the reason why it's able to do that is because there's something called information asymmetry, right? So let's say in the context of traffic, okay, let's say there's an accident, okay? In LA, this is the heat map of accidents and a lot of accidents that we have. On any given day, I do not know for sure in real time where the accident is and how it will evolve, meaning what should I do now, right? There's uncertainty. But the system planner, let's say LSCT has its route recommendation app, it has a little bit of more information than me, right? Can it use that information to nudge my behavior? What that means is choose certain routes so that we all don't end up choosing the same route. We kind of spread out, right? That is the idea of information design, basically. There is a so-called public version of information design. There's something called private version. So public version means you relay the same information to everybody, okay? And private version, which is more powerful, as you can imagine now, because we all have cell phones, I can randomize and give different recommendations to everybody. As you can imagine, that's more powerful now, right? Of course, in all of this, the challenge is, why should I, as a driver, follow the recommendation that I get. That is really the Achilles heel of this whole framework, right? So what I'm going to do now is review the framework as it would happen if we apply straight away the private information design concept from economics. Okay, so here's some formalism, right? To keep things very simple, in reality, I mean, it doesn't have to be that simple. For the sake of explanation, let's say my state of my traffic network is either A or N, where A is meaning there's an accident and N means no accident. Okay, and the accidents happen according to some rate, which is given by mu, right? So for example, if I'm traveling on this one of these routes, which is my day of travel, right? For any given day, whether there's an accident or not will depend on the frequency at which these things happen. So this I can estimate from my historical data, right? So that's mu, okay? Now, as a driver, probably from my experience, I know the heat map, okay? Meaning I know the frequency with which accidents will happen, but on any given day, I do not know exactly where the accidents have happened, at least not very quickly, which means the theta, the actual value, is not known to the driver, but it's known to the system planner, okay? Now, system planner wants to use that to influence, it's going to use that value of theta to now make a recommendation. You go here, right? And the way it's going to do that, it's through this table, right? So what that means is, if theta value is A, which is there's an accident, it's going to recommend, in this case, I have only two routes, PA fraction of drivers to take route 1 and 1 minus PA fraction to select route 2. And in the other case, if there was no accident, then I'll recommend according to this one, right? This is the policy that the system planner has in mind. And it makes this public. Everybody knows that this is the table by which I'm going to make the recommendation. That's it. Okay, again, some of you may already start criticizing some of the assumptions here, which is exactly what I'm going to do in a minute. This is how economists would pose the information design problem when applied to private route recommendation, right? This is how they would think of recommendations, okay? Now, what do I do when I get a recommendation as a driver? What I've described so far is what the system planner would do to generate the recommendation, right? What would I do? So when I receive the recommendation, let's say I receive the recommendation of taking route 1. Knowing the frequency with which accidents happen on route 1 and route 2, and knowing how the planner decides the recommendation, I form a belief that most likely there's an accident here or here, right? So there's some kind of, let's say, Bayesian assumption, okay? And based on that, based on what I believe to be the accidents where I can decide whether to go with the recommendation or go with a different route, right? If according to my belief, is still following the recommendation is the best, meaning it will take me shorter time to take route 1 versus route 2, then I'll accept the belief. Otherwise, I'll not accept the belief. So what I've described to you is essentially what, once you write down mathematically, that's what it becomes, right? So what a system planner wants to do is, wants to design this table, values in this table, okay, to optimize certain objectives. So that table is denoted by pi here. Again, we could go the detail, but that's what this is. It wants to design that table, okay? But it cannot design that table arbitrarily because, for example, it cannot have everybody go to one route because people eventually realize the planner is trying to fool us, right? Again, so the tables have to be generated so that the recommendations, when they induce a belief on the agents, they have to be optimal for them, right? So this is what is known as the so-called obedience constraint. Okay, this is the fundamental underpinning of information design. Okay, so let me be more formal. Okay, so there will be some math for a couple of slides just for those of you who want more details, but very soon I'm going to start questioning some of these assumptions. Okay, so according to the obedience constraint, if I as an agent get I, let's say I'm being recommended that you follow route I, I'll obey this route if, again, so once I get my recommendation, I form a belief on what the state is and what recommendation is being received by other agents. Again, so this is the belief that economists say the agents start following, right? So the agents are thinking, okay, if I got recommendation I, how many other agents are being also recommended that route? And also, what is the state of the nature? Because both of these quantities are going to determine my travel time, right? Because whether route 1 is as accident or not, and how many others are going to take that route or not is going to affect my travel time, right? So based on this belief, if my expected travel time on route 1 is better than every other route, then I'll follow the recommendation, otherwise I will not follow the recommendation. Okay, so that is what the obedience condition means. Okay. Now, I hope at least in words it made sense what I said, right? Now, if you kind of parse through that and put yourself in the shoe of a person who is being modeled by this, okay? There could be several objections, okay? The first objection, in my opinion, is we do not, it has been shown in simple laboratory experiments that people are very poor Bayesian calculators. I mean, this is much more complicated than what we do, right? Even for computing Bayesian probability for discrete PMFs, we are very, very bad, let alone this is much complicated than that, right? So people are not Bayesian agents, at least when they are faced with an incident and they want to respond in real time and all of that, right? The other assumption, which is kind of, so even if you assume that they're Bayesian agents, their posterior computation depends on them knowing this frequency of accidents, right? Which again, I have a mental map, but I mean, when I convert that mental map into some numbers, I mean, all of us may have different ways of translating that. And similarly, this assumption assumes that the playbook that the planner has to make recommendation, the agents also know it, at least through experience or whatever. So there are several assumptions, right? So what we wanted to do was move away from this, right? We wanted to replace that obedience condition with something that agents use simple rules of thumb, right? When I receive a recommendation, well, yesterday this didn't work out for me, so maybe I'm not going to pay attention to this, but maybe it worked out for my friend, so maybe I'll try it today, right? So very non-Bayesian kind of very empirical kind of a setup, right? So we propose a model, so we are going to propose that notion. But more importantly, we did experiments with human subjects and we saw that there has some validity, right? So that was the novelty, right? So in that sense, this is, in my opinion, one of the first work that extends the notion of obedience to dynamical and empirical setting and verifies in some experimental setting. So, so in the interest of time, I'll go quickly through the experiment design and some of the key findings there, right? So basically, we say that the agents. So this is a literature search on what related works have been done in this context. So we are not the first one to think of agents as non-Bayesian or non-rational. There have been some work done before, I mean, particularly in the economics community, right? We are different, and there are some details here. So basically, we say that when an agent gets a recommendation, by the way, the agent has, in the modern world, the agent will know its own recommendation as well as some understanding of performance of this recommendation system from the past, right? Yelp review or something like that. And I myself will be able to contribute to that. So at the end of my trip, I'll be able to give a Yelp rating, right? To tell others what was my performance using this app, right? So when an agent gets a recommendation, it sees the recommendation, it knows how this app performs so far. And on the base of that, first it's going to decide whether to obey or not. There's a certain likelihood with which it will obey. Okay, and we have a certain model for that. And if it does not obey, it's going to fall back on some choice which it would have made if there was no recommendation system in the first place, right? That is a simple model we propose, okay? So every agent has a certain preferred route, let's say, even if it's probably someday I fix this route or this route, I always come with some preferred route, okay? But then somebody gives me a recommendation, right? So either I follow it or I fall back to my baseline option. That is the kind of model we propose. Okay, and you can write down, and so that is one element of this model, right? Like how, whether I obey the recommendation or not. And then there's a different part of the model which says that, again, the star ratings are collected based on the feedback from the user, right? How do users give the feedback, right? Is there a model to predict how the users will give feedback to the system? And so this is where we say that the agents, so once I get a recommendation, let's say I follow the recommendation, and then after I follow the recommendation, I compare my travel time with what could have been if I had followed the other route, right? Because I can look at the reports, etc. And I can compare my travel time with, let's say, what I would have taken if I had not followed the recommendation. And the difference between that is going to determine my star rating, right? So if that difference is, if I ended up getting very best route, right, then I'll give 5-star rating. If I got really worst route with respect to my baseline, then I'll give a very small star rating, okay?
So what does Google Maps use?
In terms of star rating or recommendation?
Recommendation.
So previously, it was not randomizing, right? So it was, but I think they're doing some randomization now. They're not very open, of course. So one of this thing is to kind of question, I mean, it's getting to the bottom of that in some sense, right? Because there are no experiments that have been done whether people follow it or not follow and things like that. So we are trying to go from really scratch and trying to understand that part, right? So we want the agents to know their own, plus also influence them through what others are thinking through the star rating, because they already have it, right? Okay, so we can put together all of this, and basically we can write a dynamical system now, which says on a day-to-day basis, how does the number of users using one route changes on different routes. So X here is the number, X is a vector of link flows, or number of users on different routes. So in the two route case, size of X is 2, okay? If this is 3, then Q is 0.6, okay? Something like that, okay? So our model says that, so there are certain hypotheses which we say, so these are the key assumptions in our model, that whether an agent follows a recommendation or not is proportional to the star rating, okay? There's some assumption here. So what that means is I am relying more on the social notion of acceptance of this thing rather than my own individual. That's an assumption, okay, which we're going to put to test to the experiments. The second assumption is that when people give feedback, star rating on individual basis, they're computing in a way that I was mentioning, right? They compare their own travel time versus what would have been if they had followed their own judgment, right? And the last thing is, indeed, people come up with some baseline option they would have taken. This is something we call non-obedient route that they would have taken, right? Among many assumptions in our model, these are 3 key assumptions. So our analytical result is that if these assumptions hold, then indeed asymptotically people will follow the route recommendations. So that was the result, but we of course had to verify this. So here's the experiment we designed. So people come in and they have to select between one of these 3 routes. Okay, that's the option. And for each route, these are the uncertain travel times. Okay, so minutes versus percentage. What is the likelihood that the travel time will be this versus this, right? So this is the uncertainty in their travel times. Okay, and they have other information, average rating. What is the rating of this particular app which is recommending you so far, right? So this is what would happen at time t0. So they will do this over and over again. They will make these choices over and over 100 times actually. So when they start with the app is really great, they process all this information, a route is being recommended by highlighting one of the routes, in this case route 1, and then the user gets to pick one of the routes, okay? And then after picking the route, then the actual travel times are reviewed. These were the travel times. Now the user can give a feedback, okay? And once you give the feedback, the star rating gets averaged, okay? Based on all the user feedback that it has received so far, and the process keeps repeating over and over and over again. And the question is now is asymptotic, meaning over the long run, what happens? Does the star rating start going 5, or eventually this thing drops to 0? Nobody really likes this app, right? That is really what we want to see. And of course, that will depend on how we are generating the recommendation, right? So what we did was we generated the recommendation based on what the economist view of coming up with optimal recommendations, solve for optimal cost subject to the obedient constraint, right? We generated the recommendation using the classical economist way, but we're testing it on actual humans. That's what we were doing, right? And what we showed was that in this experiment, it does work out. It does work out, right? Meaning, but analytically, we said they will work out if again, the hypotheses are true, right? So these are the hypotheses which if a model has, then the long run behavior under this model is the same as the obedience constraint that we had in the thing. That is really one implication. So in the interest of time, I'll throw some numbers, okay? So here are some numbers which, so again, there are 3 hypotheses that we wanted to test, right? So we could observe, we could really see whether the person is obeying our recommendation or not, because we know what recommendation we gave and what the choice the person made. Based on that, we can compute overall population-wise what was the average percentage of following the recommendation between different. And how does that correlate with the rating that was on the screen at that time, right? And there seemed to be a very strong positive correlation between that. So that confirmed our first hypothesis, that people tend to put a strong emphasis, at least in this setting, on the star rating, right? I mean, if others are thinking so well, then probably there's something to it, right? Then remember, there was one hypothesis that for those who do not follow the recommendation, there is some kind of a fallback option that they have in mind, okay? Which is again, we can compute because we store what they pick if they do not pick our option, right? So we plotted the choices they made when they did not pick our option. And so we can compute, for example, probability, like when I recommended route 1, and if they did not follow the recommendation, what is the probability that they chose route 2 versus route 3, right? Because I can see how many times they chose route 2 versus route 3, and I can plot those values as time goes on, right? Those number of times they did that. And ideally, we should go over the long run, but for example, the fraction of times when we recommended route 1, but the user instead chose route 2, as the number of participants kept increasing and hence our data set kept increasing, it seems to converge. Again, ideally, we have to go even more, right? And this one seems to be headed towards 0, and this one seems to be headed to some constant values, right? So it looks like on an average, the users seem to have some kind of a stationary fallback option here, okay? So they strongly think that either I follow the recommendation or they have some favorite route in mind, perhaps. Again, the favorite could be randomized, right? So it doesn't have to be a fixed route. And the final thing was when the users provide a feedback, it correlates, it's predictable what feedback they will give, meaning it's going to be proportional to this notion of regret, right? That's our assumption also. And here we had mixed results, I must be honest. So what I'm showing here is a result from, which is a nicer one. So this one is from a specific individual, just one individual, participant number 21. So what we did was in this experiment, we had end of experiment questionnaire, basically asking them to answer a few questions which help us understand what was the strategy in choosing the route. And some clearly said they were just randomizing things, right? So for them, so if we included that in this, then this correlation was very bad. But if we filtered out among those participants who were really paying attention, who were very thoughtful in their answers, then there was a very strong correlation between ratings that they provided and this notion of regret that I have defined, right? So for those participants who put thought, it's predictable what feedback they will give, at least according to our model, right? So put all of this together, there is a value to the model that we're proposing, and using analysis, which is not trivial, you can again show that if this thing's happening over and over again, the app will eventually be accepted if the recommendations are generated according to this information design concept, right? So that is a long-run behavior, and which we also saw from the experiment also. So asymptotically so each participant, I forgot to say, did 100 times the same thing, and there were 30 participants approximately. So if we average the star rating, then by the time we have the last participant at the end of the experiment, it was close to 4.6, 4.7, right? So very strong predictive power. So, okay, so I think I've already spent enough time. So I'll start by concluding by saying, I think transportation is a domain where data-driven ideas, I mean, these are just two of many, many possible ones where, I mean, the data-driven concept is very fruitful. So for example, applying it to RAM metering, we say that the amount of data that you need for estimation, if your objective is to estimate the queue length, then you need sensor per every cell. But if your objective is to do good RAM metering, then you don't need so many sensors, right? So this joint control estimation provides very, very strong insights, in my opinion. And again, for the second part, we hope that we believe we are coming up with this new notion of dynamic obedience, which is much more empirical and less grounded in Bayesian rationality than what people typically assume. So we are doing more experiments right now like this, where we are playing with pricing and not recommendation, where we are trying to online learn the value of time implicitly. So again, we don't want to first learn the value of time and then do pricing. We want to directly from the data to the pricing, right? And we are seeing some interesting results from the experiment already there with human subject experiments. And so I mentioned briefly at the top of my talk that I have a company where I do traffic signal control. We have it running in 4 cities, right? Which is all data driven, and I can go at length some of the interesting stuff here, but I think I'll stop. Thank you for your time. And here are some samples. There are conference versions. These are under review, etc., but they can be obtained from my webpage. Thank you.
It's fascinating. The last piece, are you doing the experiment with students or?
Students. So it's interesting, right? So I don't know how is it at Davis, but probably similar. So undergraduates.
Undergraduates.
Undergraduates. So this is something that they really get excited about, the whole experiment design and all of that thing. So it was spearheaded by all the undergrads, the
And then
interface design and all of it, and the running of the experiments. Of course, there was a PhD student involved who designed the whole algorithm, and they are still involved. I mean, it's so every year we have a new batch of 2 to 3 new undergrads join the lab, and they just get involved in this project.
You know, I have a postdoc who now teaches at Beijing Jiaotong University. So we jointly did some experiments about departure time choice,
Yes.
but no recommendation.
Okay.
And so we have a paper in review for transported research.
I see.
At this
So
moment.
believe it or not, one of our future experiments is on departure. I already have a paper on recommendation for departure of time choice, but we haven't tested it out in experiment. So that's one of the experiments we want to do.
Yeah, and I think one of the limitation of our work is that we did not have a survey afterwards. So a lot of the behavior aspect, we kind of guessed what was at play, but we really didn't ask the people,
I see.
how, because you can see some people will just stick
Yes.
to a particular time. They just don't move at all.
Exactly.
Or some people will just tends to be choose the early ones.
Yes.
Some people choose the later
Yeah.
ones.
Yeah.
You can kind of get a feel of how risk averse or
Yes.
risk,
Yeah.
taking, but it's good to with a survey
Yes.
and to kind of
Yeah.
support.
Yeah. So we have a questionnaire that we host. I mean,
Yeah,
we
that's
put
good.
some thought into the questionnaire.
Yeah, I think that's a good strategy.
So what happens if they just always choose your recommendation?
I mean, they can choose this, so that would bias our data towards. I mean, some people did.
It's like, when I go by Google Maps, like when I
Yeah.
drive, right? I tend to use it, and when I don't use it, I get screwed. So I
Yeah.
said, okay, go back
So
to
maybe
Google.
Google is already doing well then for you, right? So
Yeah.
so
I don't want to
again,
mess around with Google
Yeah.
Maps, right?
so again, when I talked to somebody, this was way back,
Yeah.
they said that right now they give the same recommendation to everybody.
Yeah.
Okay, earlier, this was now, I think they're randomizing now. And I asked them, I mean, this is obviously at some point you're going to face a problem because you're going to say, but they say they rely on the fact that the penetration rate is low right now.
Okay.
Yeah,
And they can redo this very quickly, right? I think they're doing something smart. So this is directly addressing what if everybody starts adopting it. I mean, is there a bottleneck, right? And this is saying, well, if you do things correctly, then there is a way, right? So
the other thing about recommendation is, you could have people faking, misinformation. And
Yes.
That's a lot of these sort of rankings and
Yeah.
stuff. Like for example, you want to buy a computer and you go
Yeah.
look at the ranking thing. Now I tend to not look at the top ones, but go into the second or third
Yeah.
because some of the people can game the system.
yeah. So yeah, the rate, you are correct, especially in traffic. If I don't want people to follow my favorite route, I'm going to do this, right? So eventually, fingers crossed, we want to create an app out of this. Should be easy, creating an app out of this and just deploy it and see how it goes. So but I think the point, so I mean, all those, we're completely aware of those things. I think the point of this talk is there's a formal framework to think, this is called so-called information design, which economists have been really pushing a lot, again, in the last few years. And what we want to test out is, can we design a good recommender system based on that, at least in lab, right? And the next step is an app, of course, and that's where we'll deal with all those issues now, which will, I think what you're proposing is really questioning one of these assumptions, right?
Yeah.
When I provide a rating, is it really this concept or is something else driving me, right? And some of this.
And the first one also.
First one also, yes, exactly, right? So first one right now says that you rely primarily on what others think rather than yourself, because you think you're too insignificant as far as traffic is concerned, but to think your experience much more weight, right? Who knows whether this will hold out? We'll see. But again, I must say, right, at least because we have a formal analysis, we know if we perturb these things a little bit, we know how this will affect the results. So we have a framework to start with.
We have students with a very diverse background. They might have other questions. I know several of our students work specifically on behavior, psychology, all those aspects. Any questions from students?
Yes.
On that slide when you were talking about the spatial distribution of traffic accidents.
Yes.
Could you go into more detail on what type of accidents you think this sort of research can be most relevant in preventing? Like, are we talking about accidents from people merging on to the freeway, or these accidents on surface streets?
Right. So it's really not the type, but their impact. The more uncertain it is, the more infrequent, let's put it this way, those accidents are. I guess you're talking about this one, right? Yeah. So the purpose of this is a heat map of almost all types of accidents, even minor, major, everything, right? Anything that affects travel time, those are these accidents. So now your question is, I think that what I proposed here, will that work for every accident type that happens, right? And really, the whole concept of information design as a way of generating effective recommendation is if there is information asymmetry. If there is no information asymmetry, meaning the people know as much as I know, then this does not work. Because there's no way to kind of send people through different routes. The only way I can convince people to choose different routes because they are uncertain, right? I'm banking on their uncertainty to kind of move them towards different routes. So really the question you have to ask is what kind of incidents will lead to those scenarios, right? So if there are accidents where it's very hard for me to predict how others are going to respond to this, right? That's where I think this will very likely kind of have the most impact. I don't know if that answers your question. So it's uncertainty. There's a lot of uncertainty and unpredictability under a given accident. This is where I think this is going to have the most impact. It's more about how much information asymmetry I have with respect to the agents.
And besides the accident, I think those large event-driven congestion, that information is not globally known,
Yes.
right? You
So
start
uncertainty.
having very heavy congestion at the local level.
Yeah.
You want to use that inside the information to guide.
Yeah, exactly, right?
Yeah.
So when you cannot contemplate as a single agent the impact of something on the whole network, and hence the unpredictability basically,
Yeah.
right? So in fact, because I said we already also have a paper on information design for time of departure choice. The example that I bring up is USC games. So we have football games on campus, and we are a very urban campus. On the days when there are games, I prefer not to go to campus, right? So we get an email at the beginning of the semester. These are the days when the games will happen, and these are the times when the games will start. Nobody's coordinating when you arrive on campus, when you leave from campus, and all of that. So I'm spilling the beans here, but one of the first thing we want to try is try some of these ideas in coordinating some of this, because maybe the faculty will be more thoughtful in kind of participating in this. We'll see.
Any other questions?
Yeah, from my perspective, I noticed that you use the star rating from the used travelers.
Yes.
And I was thinking that did you consider the different sample sizes? Like, because for some routes they are more popular and they may we may connect more samples from this specific routes, but for other routes, there are very limited star ratings. So
Right.
how should we balance the
Right.
Yeah,
So I mean,
variance?
we did not. I don't remember top of my head, but I don't think so. Again, the star rating. I think what you're saying is probably a good point, right? So in our experiments, there are only three routes, right? It's a simple setup again.
Oh, I see.
Yeah, so again, there are three possibilities, right? And I don't think they are generated equally. But so the recommendations are more biased because the way we set some of the parameters here, they're more biased towards one, yes. But I don't know, maybe it's worth checking what if we change. In other words, one could always argue that your results maybe are true for this specific choice that you did, right? When let's say I skew, when I go from 3 to 5 and some of these uncertainties change slightly, because of which I start recommending route one more often than the other, maybe some of this hypothesis will fail, right? So is there a limitation to your hypothesis that there has to be a really good spread of recommendations? I do not know, it's a good question. I have to, if there are some higher order effects that play into the minds of people, right? Completely, very good question. More people we have dealing with that would be great. Again, our objective was to come up with one scenario where this thing works, right? So I know it's a very self-serving purpose, but we wanted to start from a scenario which you can analyze and which we know works in a control environment and now take it from there. But all this, I'm curious to hear all this responses, yes.
Yeah, the performance of these three routes, is very interesting because, you can always argue one route is in certain dimension better than the other,
Exactly,
right? Even route two,
Yeah.
I mean, it's more certain,
Yeah,
right?
yeah.
Yeah, it's much more certain
Much
than
more,
the
yeah,
other, yeah, so it's very interesting, the
Yeah.
choices of the three
Yeah,
routes seems to be carefully.
carefully chosen,
Yeah,
yeah. Because we wanted to induce uncertainty, right?
Right.
That was the whole idea. We didn't want like very clear, obvious choice, because again, this thing works only when there's information asymmetry between the agents and us. Was a question?
Doctor, I wanted to ask you, I'm interested, you didn't discuss this really, but I'm interested on the actual company you own,
Okay.
the traffic demand company. I guess question is, how does your company, how does it discern itself? How is it different from, let's say, Google Maps or Tesla, any of these companies that have enormous amounts of free data? I'm just curious.
Sure,
as to
sure.
what it's-
So let me be clear what we do at the company a little bit, right? So which is what Google Maps does not do, for instance, right? So what we do is we ingest data from loop detectors, from cameras, from connected vehicles, and we use that to real time change the timings of the traffic lights
Wow.
citywide. That's what we do, right? So it's not just data, but also take action on the data. And the second part is what differentiates us from the companies that you're saying. Now, I would argue, because we can do the second part, we can predict things much better than those people because we know what actions we are taking, right? So that's the response.
So
Wow,
which
so
are,
you have individual contracts with these cities?
Yes,
Wow, that's really
Yeah.
something.
which
I mean, it's
cities
already-
are?
So we Fremont here,
Fremont, okay,
yeah,
here.
and Long Beach, and two places. One in Denver, and there's one suburb of Denver. So 4 places already.
Can I ask, what is the name of your company?
It was in the first slide. Extelligent. We are looking to hire, by the way.
I'm sorry?
They're looking for you to work for them.
Maybe I'll help you negotiate the contract.
Okay. Yes.
Adding to the discussion of information asymmetry, do you not say like some 30 participant were repeatedly asked, given a scenario specific?
So we had total of 30 participants, and they all came one by one, right? So they were not all together. I must clarify, right? So again, a lot of these details were I had to go through quickly, but we had 33 participants in total. Actually, they were all undergrads, okay? Because again, maybe one could argue that was a bias. Again, we are working on it, right? Because this was all in person. This was not online because we really wanted to monitor everything and control everything, right? Eventually, I think in order to have very diverse sample, we need to go online and all of that a little bit. But this was like really in-house, and there were a few grads, but not like majority of them were undergraduates. And
From engineering, all from engineering,
all from engineering.
okay.
Okay, again, there could be bias because of that, right? So we have to be mindful as we go along, but and each one of them did this 100 times.
Yeah, so towards the end, like say by 90th or 99th time, they
Yeah.
will have a information bias, like they'll be better at making selections.
So what we did, we like usually you have to, there's a transient effect, right? So we kind of remove first 10-15 scenario samples from each one of them. We did all the standard practices in the data that I was showing, right? Our main concern was people would get bored, right? So this choice of 100, it's not the choice of 100, I think. I mean, so we were concerned that at some point this will become boring, right? So the choice of 100 was a little bit careful in some sense. We were willing to cut it down, but then we wanted enough samples. So we ended up, it turned out that eventually what mattered was how long the experiment lasted. And so nobody took more than 30 minutes to do this.
All the
Very
100
few people actually. I'm sorry?
All the 100 scenarios.
All the 100. Very few people actually took more than 30 minutes. Most of them took 30, 40 minutes, something like that. So we knew that if we go beyond an hour, at least based on the literature that we had read, then we have to start becoming concerned. So our concern was that. So we did some pilot tests, of course, internally to kind of calibrate a little bit. There were a few people who clearly were just doing this. So again, I did not mention they were paid money for doing this. So $10 for showing up and $10 for doing good performance, where internally we are tracking if they're completely randomizing versus not randomizing. So at the end of the experiment, they they were given a score, right? So in the current version of our experiment now, instead of showing the score at the end, they can live see what is the score as they go along, right? So that's and it flashes if it starts falling a certain point. So we are incorporating some experience from previous time.
So Ketan, when you're saying that a student, it just the one comes in and do the test or
Yes.
the experiment. So when you just have one person choosing the routes, how do you come up with the
Good.
travel times or travel
So
costs?
very good point, right? So again, this was a detail, right? So what we do is, so for the first few participants, what I'm going to say is a little bit, so let's say by the time we are the 40th participants, we have already collected, not 40th, by the time at 20th participant, I've already collected 19 participants' decisions by now. So we create a model for those participants' decision making. And so in addition to the person who's making a decision, we simulate how the others will be doing based on the average of the decision, what the others did before that. So for example, in the previous record, for a star rating of 3.5, and they were shown a recommendation of 2, how many of them chose this route versus this route versus this route? That's what we do.
Okay, so you use this data to guide
The historical data to kind of
the-
say, on an average, what would other participants, if they were present at the same time, would do, right? Ideally, we want to go in a multiplayer kind of a setting, right? Simultaneous. That's where hopefully the app will help to kind of do all of this.
Yeah, that's what we did is simultaneous,
I
all
see.
the participants.
I see,
in
I see,
Single,
I
and
see.
then you can have real time
Yeah.
that what their choice are, then you can
Yeah.
tell them what's the next.
Yeah, I mean, I think you need, I don't know, maybe some undergrads should be able to. do
Some
this.
don't converge, some
I
sections
see.
don't converge.
I see.
Even in reinforcement learning, that learning philosophy design you wait on you gather everybody's information, you update the learning, or you sequentially update it whenever piece of information comes in,
yeah.
right? So I think this is two different approaches.
Yeah.
Yeah.
Sure.
Well-
We're over the time. Well, let's thank our speaker again.